morning, everyone. Let's get started. People will come in as we go. My name is Venkat Pulela. I'm CTO networking at Keysight. My partner in crime, Cliff, went through a long travel, so he couldn't make it today. So I will do the presentation for both of us. So we're going to talk the closest cousin to storage, which is networking. AI is a system design problem, and then we cannot talk about one area without others, right? The whole thing gets pulled in. So let's get started. Okay. A little bit of agenda. We'll talk about the AI infrastructure and how it is scaling in multiple directions. Where is the data? Where is the storage? How does it move? If not anything, if there is one takeaway, networking, if you don't look at properly, there will be choke points, and that will affect storage. And instead of everyone blaming internet is slow, network is down, it'll be storage turn, right? And then we'll point finger at each other, right? So that's about to come, so we're going to talk about that. And a little bit about AI and why AI is different and how it affects and how we want to abstract and test and validate it, different levels of abstraction. So those are the areas we'll cover today. So this is about terminology. AI is scaling everywhere. Folks are working on scaling it in every dimension. The scale-in part of it is coming in within, how do you do things within the chip, on the board, chiplets. There are multiple architectures, wafer scale. So there is one dimension of scaling happening there. And another dimension is how do we used to build boxes, right? A unit used to be a chassis. Since then, we have moved from there to a rack is the unit for AI, right? Everything is optimized at that rack. So how do we connect things within the rack? And any large system ends up being large means large at the next level of scale. Always ends up being highly optimized, synchronized systems, and you connect them a little loosely and into a bigger distributed system. That's the simplest way of scaling anything, right? So the scale up part of it is trying to scale this first unit. How do we optimize things in the rack and load store semantics, highly synchronous system, and how far can we push that, right? While density is growing. Scale out is the traditional distributed system. How far can I go? The couple of things that are emerging are due to power, due to availability of different either space or other constraints, things are moving across data centers. When things move across data centers, do you want to extend the same abstraction across data centers? It becomes a little harder. Think of RDMA across hundreds of miles, and what does that bring and whatnot. But there's a lot of work happening there, and that's clearly emerging. And I think NVIDIA recently called it scale across, which is kind of scale up at the next level became scale across. So new areas are emerging in that. And last week I was talking to my friend Surendra Anubolu from Broadcom, and he started seeing something scale into NTN, into space, scale abroad, scale something else. So there are more scales are coming. People are really optimizing things at different levels, right? So that's the terminology. So with all that kind of huge AI infrastructure that spans all over the place, where is the data, right? So good amount of data is applications are running in the cloud, so they're gathering all the data. So your AWS has your data, and then your remote data centers have the data, and your edge locations have the data. It could be your autonomous car, it could be your branch office, it could be various things, right? And you also have some local data. So you have data spread around that. And then where is our storage? Storage is also kind of moving around. People are optimizing based on where AI is putting pressure on. So-called cloud, what we call front end, was the back end, your browser was the front end. The terminology is changing. So your cloud network became your front end. And then just that the GPUs cannot use those 100 gig links, or even actually 100 gig is pretty fast. We had 40 and 10 and others earlier, right? Just to connect the GPUs, there is a separate backend network coming up. And then things that you want to quickly back up from GPUs, you could directly connect storage there. That's one area that a lot of work is happening. And even how the AI storage is connected to the front end. Typically, these servers have multiple links, and there was a nice paper, like a presentation by Meta a couple of weeks ago at scale on how they are using all the 4 links and things like that. Some of this may look like common sense. It is just that the bottlenecks are moving and people are trying to solve incrementally. So how these AI racks and their connectivity to front end is also, there's a lot of innovation happening there also. So there is some, all your storage is there, and of course you have something in the cloud, right? Once we know where the data is and you're storing, how is this data moving, and where is the network role, and where are the choke points, right? So that is the whole point of, this discussion, right? So before you do anything else, you want to gather all your data and you ingest the data. You have, this is the 3rd day of the summit, so you have seen this said in n number of ways. You're hearing one more time from a networking guy's point of view. Bear with me. So you are ingesting the data, so where are you getting the data from, right? And like we said, you're bringing it from the cloud, and then you have various choices of where you keep all that into your tier 1, storage within your data center, basically, right? And there is, of course, with so much data moving, there is definitely a tier 1 and tier 2. There's a cold and hot, tiers. You guys are experts at it, so I'm not going to preach that aspect of it. And it still, when I talk to folks, right, at least in my role, luckily I get to talk to lots of folks, get different views. What I hear is that even the cold tiers are distributed, which adds additional complexity in modeling all this stuff. And I won't use the word benchmarking. I will say when you are trying to optimize, if your tier 2 is not local, if your tier 2, your cold tier is remote, it adds its own implications. And then when you are modeling, you really have to figure out all these ratios of how effective is your cache, and cold versus hot ratio. So some of that. So even though it's shown as it's all local, some of these things seems to be fully distributed. Some people are going through that. So just a little bit of animation on what is happening. In your public cloud or in your cloud, you have a bunch of they have their own set of protocols. How do you model them? How do you simulate, emulate those protocols, as well as how do you move the data and model it, right? And then that is what comes into your data center. So you would want to have something produce realistic traffic patterns, realistic storage access patterns on both sides. And so that is where the modeling is. You want to do some, there are agents that you can put in your cloud that could mimic the real patterns that you are going to expect. The reason for putting an agent versus why don't you do something real? Absolutely, you can always use anything real is always good. But in most of these cases, you would want something that is consistent and repeatable. So that forces, an agentic, I would say agentic. Agent is already loaded, so forget that. Forget the agentic. But having an agent which kind of reproduces as much faithfully as possible these access patterns is going to be very useful, right? And there are a whole bunch of use cases in terms of once you are moving all this data, what are you going to test, right? There are variations that are happening, either time-based or because of some other adversarial workloads. When you are ingesting a lot of data, once in a while you see a glitch. How do you identify that? So, and is there a deterioration of things happening over a period of time. There could be a security access control list somebody put in that is reducing performance of something at the system level, encryption, decryption, there are various other things that will, so you may want to keep monitoring the level of bandwidth and the level of performance that you are getting from all these storage and the data movement, right? The next stage of the whole AI pipeline is pre-processing. A lot of, this is in a way, I'm not going to define the pre-processing here, but a lot of east-west traffic happening within the data center. The servers are talking to other servers and doing a lot of processing. And then how do you make sure that you have enough bandwidth, your latencies are okay. And whole idea is that where is the bottleneck when you look at end-to-end. So you would want to model each of these stages with appropriate data patterns, access patterns, network traffic, and multi-tenancy, adversarial workloads, and security and whatnot, right? So that's where the problem is. But once you kind of ingest all that, I wouldn't say ingest, you kind of get all the data center, there's quite a bit of modeling you need to do to make sure that your pre-processing is modeled properly. So that's the next stage. And before we really get onto the training part of it, because GPUs don't work on your text, they work on your tensors. So there is a process in terms of how do you convert your text, your context, and we talked about all the KV caches. I'm not going to go into that. And then before it goes into the training and into your GPU memories for them to consume. So all these data transformations and how would that evolve and what are the implications for either in-network compute as well as storage and compute coming together, right? That is, in-network compute is making a little bit of progress while we have compute or FPGAs next to storage. There was some discussion yesterday. That area is not well explored. I wasn't explored enough, but I think going forward there'll be quite a bit of innovation there. There's a lot of possibilities there because the number of transformations that we see are too many because native data, native formats will reduce those. And in my view, more than doing compute next to you where your data is, the data transformation is the first use case. The reason for that is the compute. The funny thing about the AI problem is that you want all the data everywhere at the same time. So and for some reason, let's say I need all the data in the world. I get everything, I do something with it, I have an insight or some kind of a summary, maybe I just added all the numbers. The immediate next thing is I need to distribute it to every other place, right? So in that sense, putting compute next to your storage, compute, right, is difficult use case because you bring everything, you compute, suddenly you need the compute in the other locations and the data is needed in the other location. So when you naturally think what is the compute that is next to your storage is going to do, what's the best use case, is the data transformation. That way, I speak my language, you speak your language, but loosely describing that way. And then those transformations are the first order of compute we need to think in terms of storage, right? And how do you model that? And the reason I'm getting into some of these ideas is because more than debugging, optimization is where a lot of this modeling is very useful right now, right? Debugging at the system scale is very difficult. I was talking to somebody at NVIDIA. They're building these massive systems. Even they have the challenge of getting GPUs, and they have the challenges of debugging these large systems. How do you do that? And maybe they are seeing because they are building the large systems, right? So optimization is the view for now, and then we will get into the next level of debugging eventually. And once we get into the training, this is fairly understood. And I would say a lot of effort went into it. This is GPUs talking to GPUs, all RDMA, memory moving through, and a lot of network-related congestion control, load balancing, packet spraying, split packets into cells and distribute, all those things. There's a lot of innovation that happened recently. It's all getting into production. If you are following Ultra Ethernet or UA-Link or scale-up Ethernet, you will see all that. So this is the good news. But this is where the bottlenecks right now will shift from, oh, your network is the problem to, hey, storage is the problem, right? So some of you are going to get these calls that your networking cousins are getting right now. Again, that's my guess. So this is well understood part of it. I'm not going to go in through the whole thing. Jumping onto the inference, you heard enough KV cache. I won't describe, but a couple of things happening there is definitely specialized GPUs or accelerators for each stage. That changes the modeling part one more time, right? Last week at AI Infra Summit, the prefill stage versus decode stage GPUs are different, and how they are different, and so they're being designed separately. So that again, there the message sizes and the implication for the network. How do you move the KV cache, like the previous presentation? So that's going to change the patterns. One piece of work that is happening that is relevant in this discussion is at ML Commons. There is a discussion about describing a system of systems. How do you describe your memory within a system, right? Within a box, right? Where is your memory? Where is your PCIe bus? Where is your CPU, GPU? How are they connected? How do you describe that in a consistent way? Because that has implications in terms of when you run an application, where are the bottlenecks? If the PC, if you receive a lot of data, you're unable to digest the data, then you will push back some kind of flow control back onto your network. How does it impact, right? For that, to be able to model all that, you need to describe the system. And then you need to describe the topology so that you can describe the whole system, right? So there's some work happening there. The value of all that work is to be able to model and debug and optimize these AI systems, right? So that is going to change when on the inference side also, as this KV cache, algorithms and how that's being used is evolving, right? So how is AI unique, right? A couple of AI is unique in terms of somebody who does either performance or a quality testing validation of these things. AI is changing a couple of things. Earlier, if you were testing something, you could test your component. Let's say none of us build the whole thing. I build a piece of memory, somebody builds a router, somebody builds a NIC card, right? Earlier, the whole notion was that I can do my testing of that unit or that component or that module and be happy, and I throw it over the wall. Somebody else takes few of these components, assemble them into bigger components, and somebody who actually builds the system used to do a system test later, right? And that was fine. But what is unique about AI is that I'm not saying that the typical unit quality issues have gone away or testing is not needed, but the real bigger problems are appearing only at certain scale. So that means you need to do larger and larger scale testing and system testing earlier and earlier, right? So things work fine at a lower scale, but not at a higher scale, right? If you are designing a packet processing pipeline, the statistical distribution of traffic gave you, it didn't expose all the weaknesses of your design. Because you statistically, there are different packets coming in, they're accessing different aspects of your design, right? Whereas with AI is almost like a single application on the whole network, right? And it does one thing, it just does it, it moves the data at an X rate and whatnot. So if you have some issue in terms of, let's say packets come in and you distribute to 6 pipelines. What if there is only one flow, there is a huge so-called elephant flow is coming and all the data is hitting one pipeline, something gets exposed. And including packets, inter-packet rates and whatnot, AI is exposing a different set of problems, right? And that's forcing everyone to look at system testing earlier and earlier. And system testing is the requirement. Before you cannot say, I built a small thing, I have a storage, or I have a HBM and I tested it, it's done. It basically, it has to be tested in the context and the events and triggers of a system, of a larger system. So that's, And this thing is happening all the way from pre-silicon to post-silicon to system testing, right? So when somebody is designing, hyperscalers are designing a next AI accelerator, they are looking at how do I test this chip as part of a system. Earlier, we used to run few vectors and your design verification, you are happy. So this is definitely something unique on the AI side. So this is forcing us to look at how do you do testing at all layers, right? That means even if you have a simple Verilog of a small component, can I really run AI application on it and see what happens? And that too, can I do it at a scale, right? Typical packet level testing and transport and other things already exist. It's a well-known science. So I'm not going to delve into that. But maybe, we will get a little bit into what is happening at a higher layers. If you look at a traffic generator, let's say to test network or storage earlier, they were almost like a packet blasters. You can define certain packets and you can send lots of traffic and do performance testing. What is changing is that AI brings in a stateful nature of the whole traffic movement. You cannot send some data out unless you receive the previous data and do some kind of all reduce on it, right? A reduce operation. That means there is dependencies between the traffic and between all these individual operations. So there is no way of defining something and just repeating it or blasting it. So suddenly everything is stateful right now, right? And so the first round of testing is stateful RDMA. RDMA itself, in the past you could just create n number of RDMA frames and just blast and see what happens. But now you really need to maintain number of states, a number of Q pairs, and the scale. Then you have really 1 million node network. If we are getting there soon, I hear, or even if you have 1,000 node GPU system, how many Q pairs do you need, and how many flows are you going to track when you do all to all? So that scale of that state is a challenge, right? So the packet blasters are being upgraded to state, maintaining state, and you need to have these small state machines. You can't do full-fledged protocol state machines, but they are sometimes optimized to increase the density. So there's a lot of work there, and you have to model the transport before, if you really want to identify choke points and congestions, and how, if there is a congestion, how a congestion tree gets built, right? If there is a congestion, it spreads, right? And how does it spread, and how do you mitigate? You want to do all that modeling. You would have to do testing at stateful RDMA and transport level, right? So there is a lot of work happening here. If you go one level higher, like we said, everyone wants, if you are selling to hyperscalers, if you are not doing a full system testing on a component, I presume they won't take what you have. What you have been doing, not acceptable anymore. That means after the transport, you really have to test things at least at a cluster level and a collective communication level, right? There are a bunch of emulators that can come in and do two things for you, right? Let's say you have a server with 16 GPUs. You can put an emulator next to it that makes it look like a 64 GPU cluster. One dimension is the scale, right? Your customers want you to test at next scale, and you don't have these 1,000 GPUs with you, so you would have to put emulators around it to test, right? So one aspect of it is scale. The second aspect is to run the collectives themselves. And when you're running these collectives, because of the dependencies, and AI is a tail latency sensitive. It's not the million packets that went in properly, it is that one packet that is slow. That decides the whole, how fast the job completes and how fast the collective closes. So to identify all that and how do you visualize, those are the bottlenecks that need to be understood and debugged, right? So the next level of testing is, after your RDMA, then you go and try to do the collectives. And even if you have, I mean, I heard yesterday somebody saying that they have a 2000 node system, still they find it difficult because you have a real NVIDIA GPUs, or, and then you have 2000 nodes. When something goes wrong, how do I test it? One of the ways that is happening is that even though you have 2000, you take a small portion of it out and put an emulator, right? Which can really look into the much more details. It's too small a font for you to look at the bottom. But because you have, as part of the collective, bunch of nodes which can accurately record things at a nanosecond level, identify which specific queue pairs or which specific systems might have an issue. That's how you can kind of introduce into your large system, but it's not, you can't do it for production, but in the labs you can put in and then get into the detail and say, how come one system is consistently somehow producing the last soldier to arrive, right? Or the slowest packet, somehow one system. Maybe they have a power issue, maybe it's heating up for some reason, fan is. So how do you look at secondary and tertiary failures, right? So to find out those patterns, you can take a 2000 node system, put a small emulator, get into the details, because sometimes your real system is really good at doing your computation, doing the collective and doing the all reduce and whatnot, but it may not tell you, like the resources are not allocated to look at every queue pair, record the time, starting, ending timestamps of every flow, every packet, everything, right? So that is, that's what happens when we say, hey, do testing at a collective level. But if you don't do that, you won't be able to identify that one node or one link or one whatever that's going to slow the whole thing down, right? So this becomes very important. The last one, but not the least, is application layer, right? Nothing like running your real applications there. So there is, when you, and then there is a certain things that happen in serial, certain things that are happening in parallel. How do we capture all these compute and communication patterns and replicate it, right? Sometimes you cannot run your real applications on these emulators. So idea is, can we capture the data movements, the communication, and the compute patterns, and replicate those patterns, right? So there is in ML Commons, there is a group, Georgia Tech, Keysight, Meta, a whole bunch of folks there. It's all open discussion, by the way, right? It's all open forums, where an execution graph is of any AI application can be captured. Just like I said, infrastructure has a description that is being worked on at the lowest level. You have an application model also can be created. So you could really run one of your customers' applications and then capture the execution graph. I'm saying execution graph in a loose way, right? And be able to bring that pattern and run it on in your lab. That becomes very important. And it should encompass storage, network, compute, all that. Right? So there is work going on, you may want to take a look at that. The advantage of that is, one is debug, because your customer doesn't want to share their data. So maybe they will be fine. It's being defined in such a way that hopefully as an industry we can agree what gets captured without losing your confidential information. And once you do that, you could be changing your infrastructure models, couple of models, and see which one works. Maybe this topology is better. That's some other topology. Just looking at some presentations at SIGCOM happening, already happened, I guess, in Spain, right? People are talking about already circuit switching, right? Going back from packet switching to circuit switching. How do you model those things and test it out? So you can take real applications for debug, or you can take these, but idea is to capture that and then try different models of the infrastructure. And infrastructure could be in software, hardware, or firmware, or a cloud scale. So that the form factor is slightly different in this discussion. Form factor is another angle. But idea is that you will be able to test at each of these levels what is happening with your data movement, network, security, all that in one place, right? So there is some really good work happening there. Stepping back, I'm going to quickly summarize. So if you are trying to validate your AI infrastructure, you're kind of validating your rack You cannot take a simple storage angle or you cannot take a network angle. It is how all of them are working together in tandem. And then how do you test your bottlenecks in terms of, when you are downloading all the data from your cloud back into your data centers, you can model, there's a sequence of modelings that you need to do to kind of test your end-to-end and all the way to application benchmarking, which may not be quite relevant here, but typically when AI is being designed, I think most of the early mistakes are around security, right? People are building something and say, hey, let me build a POC. That's our traditional intuition, right? Let me build something and see where it goes, and as I go, I will build. But security as an afterthought means completely you are throwing everything away and restarting, and we see it multiple places. A simple one-line change in an access control list can throw there are ternary cams that apply these access control lists, and some of them are algorithmic. That means they are not memory-based. You don't have like n number of lines. They have some other logic which optimizes them. So one-line change could cause a huge churn in the whole thing, and suddenly your performance is something. So how do you identify those choke points at each of those components? And knowing that even a single component lead to one node becoming slow, and one node is slow, the whole thing is slow, right? So that is kind of a unique challenge that we have, right? And so basically you would want to kind of test, there's a little bit of animation you can see, right? You want to test how east-west traffic, and then where are the limits, where are the choke points, and then you want to test in parallel, what is happening, data coming, how is your data ingestion pipeline happening, and how is your checkpointing happening, and right size each of these models and test it at the same time, right? Validating AI is also about multiple applications, right? Good amount of infrastructure is moving, focus is moving from the data centers where you are doing training to inferencing, and then the neo clouds, people with lots of GPUs setting up a multi-tenant, multi-company, multi-application infrastructure for doing inference, and each of those applications have completely different access patterns. So how do you kind of test the challenges that you may face in that kind of situation in terms of performance, transactions? So there is a way of doing it. I didn't get into the details of products and how do you do all this to avoid making it a marketing presentation, but you can consistently reproduce issues that you face by replacing your real applications with these agents that look like, you can put an agent that can do NFS, but it does it slightly differently. It's not, you're putting an agent because you would want it to perform exactly same way, even though you repeat it 1,000 times, right? And that way, your cloud data, when it moves to local storage, that path is tested without too many variations. Otherwise, every iteration is so different that you couldn't identify what exactly is the problem. Whereas you want consistency, you can put agents in the cloud, you can put agents in your data center and test those paths as you evaluate. With that, I conclude this talk. Thank you very much. Any questions? Yeah, go ahead.
You're coming from a networking perspective. Have you done any work with modeling how ultra Ethernet would modify things there?
Yeah.
You could share.
Yeah. Yeah, simple answer is, I'll repeat the question. Have you done any modeling with Ultra Ethernet, right? So, yes, Ultra Ethernet brings in a bunch of things, right? I mean, of course, it's creating higher, it's doing things at the link layer, which is link level replay. So if there is a packet that is lost, instead of letting two ends of the world TCP stack realize and then retransmit, locally there is a retransmit. Even a credit-based flow control where you send only when the receiver is ready, is happening at the link level, right? And at the transport level, various other things. Simple answer is yes. The interesting part of it is you can just do the Ultra Ethernet testing. Ultra Ethernet is bunch of features, you could select few and do testing. What would be more interesting is that now that you have Ultra Ethernet, what is the implication to not only the backend network, how does that affect storage side of things, right? So, and then, what does it mean to your checkpointing? What does it mean to your ingestion? All those things, yeah. Did I answer you? So, yes. The specifics in terms of, because every vendor uses the equipment to test if the bugs they found, I cannot definitely comment on it. But people have hardware, that's a good news, right? We have recently tested 1.6 terabits per second, which is really, who thought 1.6 tera used to be the complete capacity of a switch. Now we are talking about links, right? I can't believe I'm even saying it, right? And the speeds and feeds are improving, and then AI-specific innovation is in production already. The other thing to say around that is that there is a proliferation of these solutions. So there's a lot of innovation happening at the transport layer. At the same time, there is also a tremendous progress in terms of standardization at Ultra Ethernet and UA link and things like that, right? So you still see a lot of proprietary RDMA protocols because people want to innovate. That's good. But also I see industry coming together and making sure that things are interoperating well. So maybe that would be the comment. Yeah. Yeah. Go ahead. Question is, are there any test suites to test AI requirements, right? Yes. Yeah, from a networking point of view. But the whole notion is that you cannot just do networking. The networking test suites are evolving to system. That's the reason I'm a networking guy. I just joined SNIA yesterday, or at least I sent an email. I haven't quite joined, but right, thanks to Jay and David McIntyre. He's not here, but so we had good discussion. So the reason is that AI is a system. We cannot take a networking view. That will be one comment. The second is that yes, there are systems available. So what you could do, let's say you are building a server, or even you are building a component in a server, but you your demo is a server. You could really bring a box from avoided Keysight so far, but let's say we have a box. You can put it next to it. Suddenly make it look like a 1,000 BGP peers is how it was in the past to do the network part. But now when AI comes in, it's not just the networking and routing testing you're doing. That's kind of assumed. You do that anyway. What you need is this box to look like 63 other nodes so that you form a 64 node AI cluster and run tests at the link level, you test the RDMA, you slowly progress, right? First you make sure your links are okay, one transceiver is bad or maybe one fiber is bad, things like that. And then kind of you go up and then you start doing a collective. You really run a collective communication. You do an all reduce and see what happens. Some bottlenecks will come out. Maybe there is a server that heats up. Maybe there is a server, the PCIe, some issue on the PCIe that's not allowing whatever data it received to be loaded onto the memory. So when it can't receive, it pushes back. There is a PFC, right? There's a flow control messages that go onto the networking. It's not networking anymore. It's part of the whole AI. What is the implication to your job completion time, right? The only metric is the job completion time in AI. Everything else is, you figure out, right? So there is no network, there is no storage. I would rephrase that as how do I test whatever component I have at a system level, right? If that is the question, answer is yes. So the network testers have evolved to do transport testing as well as collective communications. Like I said, you could even capture an application, bring back and replay and see how that works. You could be, if you are a network testing engineer somewhere in some company, and you had your boxes and you had your network test suites and you were testing that, you are happy. Suddenly your boss comes and says, hey, make sure you do AI testing. How do you do that? So those things are available where we have these, emulators that will come in and then connect to your box and suddenly start doing AI-centric testing, right? And AI is bringing out unique problems which you cannot just do, your packet tests anymore, right? Because at scale. So that is one AI aspect. Second is the scale part of it. And the other requirement could be, yeah, you are testing it, but can you test it as if it is part of 60,000, 64,000 GPUs, let us say? How do you do that? The solution to that is you take some real components, you surround them with some emulation, you surround them with some simulation. So your system is 64,000 nodes, but you can't, nobody has budget, even NVIDIA guys sometimes I hear I don't have a hardware, which is strange, but that's a real problem, right? So what you do is you really want to test on real components, real ports, real buffer sharing, real congestion. So for that you put some real components so that that aspect of it gets tested. And then you surround with emulator. Emulator, I'll define simulation emulation, right? There are many definitions. Simulation is, it acts like a duck, it quacks like a duck, so it's a duck, but what is inside could be whatever, right? And you could do quite a bit of it in software, you could scale, you could put 1,000 things in it, right? The emulator is where it acts like a duck, quacks like a duck, but if there is a problem, you can go in and see this. So the implementation inside is not the real thing, but is something so that if there are issues, you could uncover, surface those issues and debug and find some insight. So a simulator or emulator can never replace real. But simulator is a high fidelity simulation, and they can be sometimes a little faster or whatnot. So you would kind of build these large systems with some real components, some emulators and some simulators. Thereby you are doing not only the functionality testing, but you are testing things at scale. The real problems are showing up only at scale. There's a lot of issues that came up in the industry, I won't name the companies, right? Because they're all doing system level testing, and that's why you see hyperscalers asking everyone else, do system testing now on whatever you are doing, or run the whole AI test and then give me, whatever that AI means. And that AI test, to answer your question, when you say AI test, so this is how you should think, not like, hey, does my network would stop at link and packet and transport, isn't it? Whereas collectives and applications you cannot call it network. This is really an AI test, even though AI is everywhere. So you would want to, those tools exist. You can model your storage plus compute plus network. You can model all that stuff and try it out and see, are you AI ready? Even if you're doing a small memory chip, you can test it in this full context. Triggers and events need to be that way, right? It is what happens when there are 64 K GPUs, because maybe you need to, really, talk to 1 million GPUs. That means you need so many queue pairs, so many flows. Maybe you have a flow table limitation. How would you surface that problem? So you can do that kind of scale testing, right? Long answer, but hopefully you got what you want. Any questions? No? Once, twice, thrice. Okay, done. Thank you. Thanks, everyone.